Thank you very much. Thank you for having me. Good afternoon, everyone. In addition to having a doctorate degree in geology, I also have a master's degree in science education and a bachelor's degree in geology from the University of Florida, our very own University of Florida. How about that? And I, as was mentioned, am here to talk to you, or to ask the question, does modern science falsify Vedic claims about the age of the Earth? The answer is no.
Thank you.
There's an asterisk, so you can all go home now. No, there's an asterisk there. I hope you see the asterisk. And we will revisit the asterisk in a few minutes. Well, let me just, in 15 minutes to be exact. The next question, why are we talking about geology in a conference on science? The answer to that question is, I don't know. Actually, the answer to that question is our friend Bob here has been hounding me for years to engage in this topic. And, you know, geology is about rocks. I study rocks and water. It doesn't necessarily directly lend itself to discussions on consciousness, but it is human nature to ask, who are we, where are we, what are we doing here? And our most immediate field of reference for doing that is the Earth. So I'm going to discuss this topic on a factual content basis, but I'm actually using the topic as sort of a case study to how to think scientifically about these questions. Who are we? Where are we? What are we doing here? And so I put together this little diagram. Starting here in the most subtle form here is consciousness. We are all conscious beings. Our consciousness then leads to sense perception. Sense perception starts to materialize in even more, what's going on with my clip here? Starts to materialize in an even more gross form through observation. So perception is sort of like a blanket background awareness. Observation is, as we heard this morning from Dr. Wrights, is focus. We're shining a light on a specific thing. We're wanting to see specifically how something is working. This then bridges into the scientific method. The scientific method is something that has been codified over centuries. We are not the proprietors of the word science. We do not get to define what science is if we want to be taken seriously in a scientific context. This is a well-defined thing. The scientific method is a well-defined thing. And science is not necessarily equivalent with knowledge. I think this is an important point. Science as a body has factual content in it, but more importantly, science is a process for understanding our environment. And that leads then to empiric knowledge. Here on the lower end of the spectrum, these things are all personal, subjective, and qualitative. We've discussed this sort of ad infinitum over the last night. And today, as we move up in the chain, these things here, this involves quantification and consensus. Science also is a consensus building process. It's not that I have an idea, here it is. Science involves peer review, and it involves groups of people coming together and collaborating to define the empiric knowledge that we're looking at. What is the bridge here? I think this is where the focus of much of our conference is how do we build this bridge from observation, which is subjective and personal, to the scientific method. And in many ways, this is done through mathematics. Oh, I'm gonna click again. Mathematics is a language that sort of builds a level playing field for how we observe things. The way I add 1 and 1 together is going to be the same as the way you add 1 and 1 together, regardless of how we perceive red and blue. So mathematics is sort of an underpinning language that builds this bridge between observation and the scientific method. And I'll talk more about that in a moment. To get into some of the factual content about the scientific views of the age of the Earth, I've just put together a little history lesson. Unfortunately, I don't have the notes of this PowerPoint. Anyway, natural science and natural philosophy used to be very tied together. The idea that science and religion were co-collaborators in a search for truth is not new to this room. It actually was very much in vogue during the late Renaissance, the beginning of the Industrial Revolution, and the original people who first started to try to date the Earth were all members of the clergy. The most famous one here is the Bishop James Ussher, who was the Archbishop of Ireland in the 1600s. A lesser known guy, but working around the same time, was a man named by the name of John Lightfoot. They both took the Bible and tried to reconstruct biblical chronology to find out when the Earth was formed. Ussher was very exact. He said that the Earth was formed on the evening of March 22nd, 4004 BC. And I know there are some Jews in the room, of course. In Judaism, the day begins in the evening, so the first thing we get to do every day is go to sleep. And so that's why it starts in the evening here. Lightfoot worked around the same time as Ussher. He came up with a slightly earlier date. Both of these dates are extremely recent, and we actually have archaeological evidence and other scientific evidence that would falsify these claims. This was not just a matter of looking through the Bible and so-and-so begat so-and-so and lived so many years. This involved very careful studies of classics and astronomy and history. And so this was actually, at that time, given the information available to these people, these were actually very rigorous academic undertakings. Fast forward a couple hundred years, we get the very well-known Baron Kelvin, William Thomson, most well-known for discovering the temperature of absolute zero and the Kelvin temperature scale. But he also made a couple assumptions about how the Earth was formed. He hypothesized that when the Earth formed, it was a completely molten ball of rock. And then he calculated, based on known thermodynamic principles of the time, how long it would take the Earth to cool under those conditions. He derived an age of about 20 to 40 million years old, which, damn this thing, 20 to 40 million years old, which again, according to modern geology, is actually a very young age. He did not have accurate information concerning many of the physical properties of the rocks. They did not have, for example, calorimeters. A calorimeter is a machine that measures the heat capacity of a substance. They didn't have those in the 1800s. They weren't invented until near the very end of his lifetime. They also had no knowledge of radioactive decay of substances, so he drastically undercalculated the heat of the Earth, which led to this artificially young age of the Earth. With the discovery of modern radioactivity, and in the inorganic scientific context, this is often attributed to a guy named Ernest Rutherford. Of course, we know many other people who were working on radioactivity at the time, the Curies and so forth. He discovered that these things deteriorate over time and that radiogenic materials have half-lives, and I'll talk about half-lives in a moment. He suggested to this guy, B.B. Boltwood, who I think worked at Yale, correct me if anybody knows if I'm wrong, he suggested that we apply these principles of radiogenic decay to absolutely date the age of rocks. Previous to this, we could only have relative dating of rocks. We could correlate strata, geologic strata across the world, and we could see where strata lined up, but we couldn't place any absolute ages onto these stratas. He suggested to his friend Boltwood, hey, you should try to do this on some rocks and see what happens. And he did that. And that led to the development of radiometric dating processes. So radiometric dating, this is the equation for radioactive decay. If you know anything about mathematics, this is a standard exponential decay equation where y here is what we measure of the mass of a particular isotope in a rock sample or a water sample or whatever you have. Y sub zero, why not, as this, why not, I didn't do that on purpose, represents the initial mass of that isotope in the rock. And we assume, so there's an assumption here, we assume that that's always full. And then E is the natural logarithm, K is the radiogenic decay constant. I'm going to return this thing to Office Max as soon as this talk is done. K is the radioactive decay constant in T is time. So if you know K, and you know Y, and you know Y naught, you can solve for time. And that's how things are dated. I'm going to this graph down here in the lower corner, we've all heard of the periodic table of elements. This is the periodic table of nuclides. And so this has not only elements in it, but it has all of the possible isotopes of all of the elements that we know on it. I don't know if you can see it with the resolution, but there's a black line that runs down the middle of that graph. That black line represents stable isotopes. Those are isotopes that will not decay. Iron, for example. Silica doesn't really decay much. And then the color coding on either side represents the type of decay that these elements undergo as they become stable. Just above that, we have, this shows the principle of a half-life. In an initial state, everything is what's called a parent isotope. I'm going to talk about uranium isotopes in a moment. And then as the uranium decays, it creates what are called daughter isotopes. Uranium has lead, different isotopes of lead as a daughter isotope. And you can see after one half-life, you have half as much uranium, and the other half of uranium turned into lead. And then after two half-lives, and so on and so forth, you get this exponential decay function. These are some down here in the bottom. These are some common radiometric clocks, as they're called. And you can see if you have a rough idea, again with this thing here, let me see if I can do this. If you have a rough idea of how old something is you want to date, you can pick the right clock. When we date, for example, in an archaeological context, a mummy or a ruin of something, we typically use carbon dating. As we go down the chain, you can see down here uranium, this is the 238 isotope of uranium, decays to lead-206, and this has a half-life of 4.5 billion years. So this is a very useful radiogenic clock for dating things that we believe to be very old, like the Earth. Putting all this evidence together, up here we have some macroscopic pictures of the mineral zircon. Zircon is a very useful element for uranium dating because sometimes the zircon in the element is replaced by uranium, and you get this decay line here. This is called a Concordia line. If you have rocks and they all plot along this line, you can easily plot where the age of it is. If they don't all plot a line, you have a thing called disconcordia, which I won't get into now. You can ask me about it later because I'm running out of time. These are some microscopic zircons that were found by a professor here at the University of Florida in India, in the Simbhu craton. He found a zircon in these rocks that was over 4 billion years old. And here we have some pictures of very old rocks. This is in the Northwest Territories, up by where I live. This is the Acasta gneiss. It's been dated repeatedly by many different researchers to be over 4.2 billion years old. That's what the GA stands for here, gigaannum. Below that is the Jack Hills in Australia, where they found zircons that are over 4.4 billion years old. But the real evidence lies in the middle picture here. This is a meteorite, a very particular type of meteorite called a chondrite. Chondrites are believed to have undergone no chemical differentiation from when they formed, and therefore are believed to be the oldest pictures of the solar system that we have. Below that is a chart of where ages of these chondrites plot, and you can see them all clustered at around 4.5 billion years. And that's why modern science says that the age of the Earth is 4.5 to 4.6, 4.54 to 4.56 billion years old. Comparing that with the Vedic version, many of us may be aware that the Vedas speak about time in cycles. And so there are sets of cycles here. I'm not going to go into too much detail about this because I think it's familiar to many of us. But basically we have yugas. The yugas add up to a Maha Yuga. 1,000 Maha Yugas equals a day of Brahma. A day of Brahma is about 4.3 billion years old. So that is kind of close, not exactly close, but pretty close. However, we're not finished with the day of Brahma. We're about halfway through it. So in reality, we're at about 2.2, 2.3 billion years in this current age of Brahma, current day of Brahma. If we look at the whole span of the life of Brahma, we have 100 years of these day and nights. Brahma will live for 311 trillion human years. And so does modern science falsify that claim? We're about halfway through Brahma's life right now, 155 trillion years. Does modern science falsify that claim? No, it doesn't. Not in the same way it falsifies the claim that the Earth is 6,000 years old. I can show you so much evidence that'll disprove the idea that the Earth is 6,000 years old. I can't show you any evidence that would disprove that it's 155 trillion years old. So how do we reconcile these things? The short answer, I don't know. Let's think about it. There's a couple issues when we want to compare with the Vedic cycle. We need to ask, where in the Vedic cycle are we trying to compare this to? Are we comparing it to a day of Brahma, a day and night of Brahma, the life of Brahma? I don't know, you need to pick your battle. On the scientific side, there's always the question asked, how have constants of radioactive decay changed over time? Well, we can say that if they've slowed down over time, meaning they were faster in the distant past, they would have given off a lot of more heat per unit time. And so the Earth kind of would have been cooked if they were a lot faster than they are now. If they're a lot slower than we are now, we would be receiving artificially young ages of the Earth, which would support the Vedic hypothesis, but we don't know. Since these radiometric clocks have been generated, we have not observed any significant statistical change in their rates within human time spans. So here's another question for you to take home and consider. If the Vedic claims are true, what sort of evidence would we expect to find? And what kinds of tests can we develop to uncover this evidence? And this is kind of the take-home message that I have for you. And then here we have my asterisk again. Until a suitable means of testing the Vedic hypothesis can be developed, the Vedic claim is not a scientific claim. Science needs to be a testable hypothesis. That doesn't mean it's right or wrong. It means it doesn't fall under the purview of science as it's commonly defined in our world. So we should be aware of that when discussing philosophy with people. Are we discussing philosophy or theology, or are we actually discussing science? And the same is true with studying consciousness. What are the hypotheses? What are the reliable and valid tests to prove those hypotheses? And what predictions can those hypotheses make? Until we are able to formulate our ideas about consciousness in these terms, I don't think it's accurate to be talking about the science of consciousness. We're still dealing with philosophy and theology. So I leave you with this little bit of a challenge, how to bring all of these discussions we've been having today deeper into the realm of science where we can test and measure these things, if that's our intention. Personally, I don't care. We'll keep chanting Hare Krishna.